Hello, this is the VISIT Virtual Institute for Satellite Integration Training module on Mesoscale Convective Vortices. I'm Scott Lindstrom from SIMS. The objectives of this training are to show examples of satellite imagery that indicate a MCV has developed. I want to describe the environment that is favorable for MCV formation and persistence, and maybe give some guidance on how to anticipate their development. And I want to discuss the potential effects that an MCVs can have. In other words, why do you want to pay attention to them? Just a little history first. These were identified from satellite imagery in the early 1980s. Sometimes if you go way back, you'll see them identified as NEDIs. That was in reference to Ned Johnston, who was at the forecast office in Milwaukee for a very long time. But in the early 80s, he did a master's thesis at the UW-Madison on these features. Typically what happens, as shown in the middle here from the 1982 imagery, is that a cirrus shield collapses and it reveals an MCV. You can also see the circulation underneath the cirrus canopy before it collapses by looking at radar. Why are these important? MCVs are spinning features within a moist atmosphere, so they provide additional vorticity, shear, moisture, and instability that can aid in new convective development. And think about how they're also going to be changing the shear profile. Noticing that an MCV has developed when the models have not predicted it, that typically means you might have to do something to your forecast. So the formation of an MCV might signal that revisions are necessary. Here's an example from 2016 where we have 24 tornadoes in Indiana and Northwest Ohio. Those extended up into Southwest Ontario as well. But you'll notice that they're all outside of the slight risk area. Why were there so many tornadoes outside the slight risk on this particular day? Well, because the title of this slide is what might happen if an MCV forms unexpectedly, you might think that this is related to MCV. Here's how the slight risk evolved over the course of the day from 12Z to 13Z. You'll notice it was pretty much the same. And it started to change at 1630Z and at 20Z. And notice in the 1630 Outlook write-up, they mention the potential mesoscale convective vortex over northwestern Illinois. So at 12 and 13Z, that particular feature hadn't become noticeable, but as the cirrus canopy erodes around sunrise, it becomes more noticeable, and you see how the slight risk evolves once that is obvious. The mesoscale convective discussion from later that day also mentions the MCV, surface heating that's just ahead of the vorticity that's associated with this remnant convectively generated or enhanced low to mid-level cyclonic vorticity center. Dynamics associated with the MCV are going to maybe influence the weather later in the day. Here we have an hourly imagery from GOES 13 because it's 2016. So the MCV is moving toward the region where tornadoes occurred. How is that circulation altering the low-level moisture and shear? That's something to ask yourself. And you'll notice how it's also helping force the development of the tornadoes that are then producing the severe weather outbreak in Indiana and Northwest Ohio and up into Southwestern Ontario. So on this particular day, knowing that that MCV was there might have helped your situational awareness for subsequent convective development later in the afternoon. What are some characteristics of MCVs? These are warm core cyclonic circulations that form within the stratiform precipitation region of a nocturnal mesoscale convective system. So you might expect that diabatic heating is very important to their presence. They're fairly deep, low to mid tropospheric structures. So from, say, 700 up to 300 millibars, with a vorticity maximum and maximum winds in the mid-troposphere around 550 to 600 millibars. This cyclonic circulation, they're always cyclonic, becomes apparent in visible imagery as the cirrus canopy of the parent MCS dissipates. The environment controls whether or not the MCV is going to persist with time. First of all, for one to initiate, you need environmental conditions that are similar to what you might see with a tropical cyclogenesis. Small values of mid-level wind shear and ample moisture. If you have an atmosphere that supports MCV evolution today, because it's slowly evolving, you might have the same kind of threat for an MCV tomorrow. For an MCV to persist, you want the MCV to move toward instability and moisture. So let's say you are in a forecast area with an MCV obvious upstream of you, but you are in a region with fairly high shear. Will that MCV affect you? Probably not, unless you have an extraordinary amount of instability and moisture. And if you don't have moisture, you might have the MCV persist if you have extraordinary low values of shear. So there's a balance between those two things. For an MCV to dissipate as it's approaching you, if it's moving towards stability or dryness or high shear, that's going to suppress any new convection. For an MCV to persist, it requires convection so that mid-level latent heat release will continue to provide energy to the mid-level vortex. So here's an example with an MCV over west central Texas, and we have wind barbs plotted, and we also have contours of Cape. There are factors here favoring persistence of this MCV. If it's moving from west to east, it's moving into a region of fairly low shear and a region of high instability. So would you expect this MCV to persist? Yes. So it did persist, and it produced new convection over north central Texas. Here's an example from June of 2019 where an MCV helped in the development of a wind and hail producing convection over Missouri and Illinois. And you'll notice in the discussion from the MCD, an MCV from earlier convection centered over southwestern Missouri will move eastward across southern Missouri this afternoon. And they talk about how moist the atmosphere is and that at least scattered thunderstorms are expected. So here we have the animation of that particular feature. So you see how it's moving from west to east. You can see gravity waves in the low-level cumulus field that seem to be related to the circulation. And then you'll notice how the convection forms around the MCV, and there are also wind and hail reports indicated on this particular animation. I'll let that run through a couple more times because it's a really interesting, I really like how you see the gravity waves propagating away from the center before the convection forms. So if you're forecasting here for the boot heel of Missouri and you see this MCV moving toward you and you have abundant moisture, you need to look for low-level convergence fields to help you identify where the convection is going to initiate. But you can expect that the extra vorticity and the extra moisture associated with the MCV is going to help. Here's another example from even longer ago. This is from 2007, but I really like this tiny little MCV that's propagating southward over Minnesota. So what can you guess about the environment that it's moving through? There have to be low values of mid-tropospheric shear and abundant moisture. And if we look at the environment, on the left-hand side we see surface dew points in the 70s. This is in late July of 2007. And look at the low values of plotted wind shear. This is the 700 to 400 millibar speed shear over Minnesota and the Dakotas. Very low value. So that kind of explains why is it able to persist with time. If you see an MCS overnight and it's upstream of you, what should you be asking yourself? Is the atmosphere between you and there, where you see the MCS, is there low shear? Is the atmosphere between you and there very moist? Does the radar show a mid-level circulation in that MCS? Can you see any indication in the satellite imagery that maybe an MCV is emerging as the cirrus canopy erodes in the morning? If you're answering yes to most of those questions, you have to ask yourself, does the model predict an MCV? Because it certainly looks like the conditions that support an MCV are present. There's low shear, it's very moist, there's a mid-level circulation. If the models aren't predicting the MCV, you really have to ask yourself why not. And maybe you have to prepare for making a quick change to the forecast. I've mentioned a couple times that the environment that supports an MCV is very similar to that to a tropical cyclone. If you have an MCV that moves out over the warm water of the ocean, it can transform into a tropical cyclone. That doesn't happen a lot, but there was a recent example with Tropical Storm Barry over the northern Gulf of Mexico in 2019. These are 700 millibar vorticity fields taken from the SSEC SIMS tropical weather website, and they trace a circulation center over the course of 10 days before it entered the Gulf of Mexico. So I've put X's on top of this image to show, kind of trace out how that circulation center is moving. Starts in Kansas, moves into Missouri, then southeastward into Alabama and Georgia before emerging in the Gulf of Mexico, where it becomes a tropical depression, and then Tropical Storm Barry. I'll let it run one more time so you can trace it out. Because it had this coherent structure that could be followed, as I'll show you on the next slide, NHC was monitoring it because the forecast models all took it out over the Gulf of Mexico. The atmosphere had very low shear. The Gulf of Mexico was suitably warm, so it did support tropical cyclogenesis. So we had outlooks that looked kind of like this, where we had the motion indicated and whether or not the probabilities were, medium or high. So at the very end, there were pretty high probabilities that a tropical depression would form, and it did form and then became Tropical Storm Barry. Here's an animation. I'm going to let it play for a little bit, but you see the convection initially in Kansas, moves into Missouri, and then it dives southeastward into Tennessee, Alabama, and Georgia before emerging out over the Gulf of Mexico. Again, this is early July 2019, so waters over the Gulf of Mexico were suitably warm that a tropical cyclone could form, and because you see this MCV, you know that values of shear are fairly low and there's abundant moisture. Here's another example. This is from 2011. This is in May, so late May, early June actually. And we see an MCV that starts out over the Midwest, moves over the Atlantic Ocean, then backs southeastward into the Florida Panhandle, and then keeps going into the Gulf of Mexico. For this particular one, there was not a tropical cyclogenesis, probably because the shear was a little bit too strong in the Gulf of Mexico, or maybe the waters weren't quite warm enough since it was late May, early June. Just a couple of summary slides now. For a mesoscale convective vortex, you need an environment that has low shear and abundant moisture. If an MCS is losing its cirrus canopy around sunrise, pay close attention to see if an MCV might be left behind. Before the cirrus canopy is gone, you can be looking at radar too to see if there's mid-level spin. And if you have low values of shear and a lot of instability so that convection can be maintained, the convection is important because it is releasing latent heat. It's going to sustain the mid-level vortex that is causing the spin that's making the MCV visible. If you have all of that, you can anticipate that the MCV will persist, and if you have a model that does not have an MCV in it, you probably need to make some kind of forecast revision. There's some additional training on mesoscale systems that are linked. You can click and see a training with Andrew Moore on MCSs, more reviews on MCSs, and some additional blog posts on MCVs, just to get a feel for what they look like from satellite at those 3 links. If you want to contact me, my contact information is shown below. Otherwise, thanks for listening.